right, last topic for Unit 4, intermolecular forces. So, adjacent molecules do interact with each other. All right, and this leads to properties related to things like melting point, boiling point, stuff like that. You'll know you've got this when you can define the different types of intermolecular forces and rank them based on strength, or be able to kind of explain based on a given molecule what type of force it should exhibit. All right. So, carbon dioxide, CO2, is a gas at room temperature. And glucose, C6H12O6, is solid. All right. We know this. We're familiar with these things. But what's the underlying reason why? All right? Is it just the fact that carbon dioxide is smaller? All right? Is it the fact that there's hydrogens in there? Like what's going on? Why is glucose solid at room temperature but carbon dioxide's not? So, the reason behind this, the underlying cause, is not the bonds themselves. These are both covalently bonded molecules, but the intermolecular forces between neighboring molecules. All right? Now, keep in mind that these intermolecular forces are not considered bonds, even if they are named so. All right, the only bonds that we've discussed and you need to know about are ionic bonds and covalent bonds. All bonds are much stronger than intermolecular forces. All right, but intermolecular forces do affect the properties of, when you have massive amounts of glucose molecules, how it reacts to things. So, in order to understand intermolecular forces, you really need to know the concept of polarity. So, when you're dealing with covalent compounds, are we dealing with transferring electrons or sharing electrons? A little review here. You should be saying share. All right. Now, sometimes our atoms, they're not always the best at sharing. Some of them need to go back to kindergarten to learn how to do this right. All right, sometimes it's uneven. Certain atoms are better at hogging the electrons than others. All right, and this comes from this concept that we covered in Unit 3, electronegativity. So some atoms are better at trying to take electrons from other ones. All right? These atoms aren't being successful because it's a covalent bond. It's just, you can think of it in terms of the sharing. It's like, all right, well, I get the electrons 23 hours out of the day and you get it 1 hour, sort of thing, instead of it being 12 and 12. So in this graph here shows you the general electronegativities, like fluorine is the biggest hog of them all. Fluorine has a really high electronegativity. So anything that is covalently bonded with fluorine, you can expect that those electrons are almost always around the fluorine and not so much around whatever it's connected to. All right, oxygen is the next biggest one. All right, nitrogen's in there too. But you can kind of see these top right corner of the periodic table. Those guys are the heavy, non-sharing, most likely to cause a polar bond. So, for example, what'll end up happening if you've got hydrogen and oxygen bonded together, the 8 electrons are probably going to be around the oxygen most of the time, which makes this end of it kind of negative and this end of it kind of positive. All right, so you don't have full charges, which is why it's still a covalent bond, but you just have the oxygen tends to get the electron more often, so there's a slight negative pole on the oxygen end of things. All right? So, molecules will be polar if there is a difference in their electronegativity. All right? So, we know if you look at hydrogen and oxygen, definitely that's going to be polar. There's a difference in your electronegativity there. But looking at nitrogen and chlorine, those two are equal in electronegativity. So that actually wouldn't be polar. Right? So also, if you compare chlorine and chlorine, two chlorine atoms are going to have the same electronegativity. That's not going to be polar either. All right? But hydrogen and fluorine definitely will, because those are going to have different electronegativities. Carbon and hydrogen, kind of. All right? There's not much of a polarity going on here because while they are different, it's a very small difference. You can kind of also pay attention to the shade of the boxes here. They have the same shade of pink. They're not far enough to cause an issue. And then hydrogen and nitrogen, H2 and N2, those guys wouldn't be polar at all because they are the same molecule. They're the same atom. Okay. So the 3 intermolecular forces you are responsible for knowing, this is a good note-taking slide, is dispersion forces. All right, so these are the weakest of all intermolecular forces, and these are the types of intermolecular forces that occur between non-polar molecules. All right, so if you think back to the last slide, this is going to be like that nitrogen chloride, the nitrogen trichloride, where they had the same electronegativity. They could experience dispersion forces. Or hydrogen gas molecules, nitrogen gas molecules, oxygen gas molecules. All right, they can experience dispersion forces. Dipole-dipole interactions, or even dipole-ion interactions, they're kind of a middle strength. All right, and this occurs between polar molecules. All right, so this is because you're going to have that kind of partial negative, partial positive end. And that's going to create a little bit of an electrostatic attraction between adjacent molecules. All right, this is medium strength. The last one here, hydrogen bonding, and this is why earlier I mentioned these are not bonds. This is very poorly named. This isn't an actual bond. But hydrogen bonding is a very strong form of dipole-dipole interactions. All right, still weaker than the bonds we've talked about, covalent and ionic. But hydrogen bonding is specific. You have to have one of these 3 bonds inside the molecule in order for this intermolecular hydrogen bonding to occur. All right? So you have to have hydrogen bonded to either a nitrogen, an oxygen, or a fluorine. And this creates really strong dipoles. All right, you're going to have the oxygen or nitrogen or fluorine end is going to be not a full negative charge, but a big partial negative charge. And then the hydrogen end will be a bigger partial positive charge. So that'll create a strong electrostatic attraction between adjacent molecules. All right, so make sure you can distinguish these, tell them apart. All right, and make sure that you can rank these. For example, you might get a question like this. Rank the following in order of increasing strength: covalent bond, dispersion forces, dipole-dipole forces, or hydrogen bonding. All right, so if you took good notes on the last slide, you should know that, all right, covalent bond is going to be stronger than all of these intermolecular forces. So if I'm going in order of increasing strength, that means covalent bond should be last. All right, so I can automatically knock out B. Covalent bond is going to be at the end of our thing. And then my weakest intermolecular force was dispersion forces. So that needs to come first. So I can get rid of A. And now it's just getting these in the right order. So dispersion forces was weakest. Next strongest, the medium strength one, was dipole-dipole forces. The strongest intermolecular force was hydrogen bonds, and then covalent bonds are stronger than that. So C is your right answer. And again, pause if you need some time to think this one through. But it says, which of the following explains why iodine is a solid at room temperature? So looking at this, it's, okay, I need to figure out, so what kind of intermolecular force does iodine experience? Well, iodine is an iodine atom connected to an iodine atom. So they're both the same thing. So they would have equal electronegativities. So they would be nonpolar. So these dipole ones, definitely not it. Hydrogen bonds require hydrogen attached to oxygen or hydrogen attached to fluorine or something like that. So that doesn't work. And there's also, if I remember my definition of dispersion forces, that's the intermolecular force between non-polar molecules. So, if you have questions about this, if anything's not making sense, please come get help.